So in this video, what I want to do is walk through a hydrolysis reaction one more time. Talk about the 3 steps that we established in the previous video. And as we work through these 3 steps, I want to highlight some really important key features in this reaction. And these key features are things that you can be on the lookout for to determine if a compound is susceptible to hydrolysis through this mechanism, through this pathway. Okay, so remember the very first thing is we have a water molecule lining up with a carbonyl, right? So we have this carbonyl right here. Remember the carbonyl is a carbon with a double bond oxygen to it, right? So this is a carbonyl, okay? And it's this carbon at the center of our carbonyl that tends to be susceptible to a hydrolysis reaction because in the first step we're able to push electrons up to this oxygen, right? So you have to have this double bond present to be able to push electrons up to this oxygen. Okay, so this is one of our key points. So number 1 is we need a carbonyl. If you don't see a carbonyl, then you don't have a way to push electrons. You don't have a place to put electrons during that initial nucleophilic attack. Okay? The other thing that you're really kind of looking for is that adjacent to the carbonyl, you have to have an electronegative atom. Okay? So we need to have an atom adjacent to the carbonyl. So here it's nitrogen. And this atom adjacent to the carbonyl needs to be more electronegative than carbon. Okay, so we need to have at least 2 electronegative, I'm going to put that En, so 2 electronegative atoms attached to the carbon. Okay, and really the only 2 possibilities we have are oxygen and nitrogen. Okay, so that's why it's really only esters and amides that are susceptible to this hydrolysis reaction. Okay, so this is why we can only do ester or amide. Okay, so those are the 2 big requirements for this very first step. Okay, and I'm going to go ahead and erase some of this stuff here so that's not in the way and distracting. Alright, so as we know, in this first step, we have a lone pair of electrons on our nucleophile. So this was the molecule that was partially negative, and it seeks out the partially positive carbon, our electrophile. Okay, and we form a bond between our nucleophile and our electrophile, and in the process, these 2 electrons that are part of the double bond get pushed up onto this carbonyl oxygen. Okay, so in this first step, the product is now this, we call it an oxyanion, this oxygen that has a -1 charge. We still have our nitrogen attached with a lone pair, but now attached to this we have a water molecule. Okay, one of the lone pairs from water has become this covalent bond. So this water now has a +1 charge. This oxygen does. Okay? So that's our first step. For the first step to happen, we have to have a nucleophile. Right? That's something that's partially negative, and in hydrolysis reaction, that's always water. Okay? We also need to have a carbonyl that has at least 2 electronegative atoms around it. Okay? So for our purposes now, that really tends to be either oxygens or nitrogens, meaning that the functional group that's susceptible to hydrolysis has to be an amide or an ester. Okay? We know that in our second step, we have a lone pair that reaches out and grabs this proton. When that happens, the electrons in the bond between the O and the H get pushed over to that oxygen. Okay, and the reason that we do this is so that we can move the positive charge from our oxygen from the water over to this atom that's adjacent to our carbonyl. And that's really, really important because in the next step, when we reform our carbonyl, we break only one bond. Okay, so I'm going to go through an example here of what would happen if this compound were to proceed without moving the positive charge. Okay, if that were to happen, so the lone pair from our oxyanion would fall back down, making our double bond. Right? We know that when that happens, we now have created a carbon. Right? This carbon in the middle here now has 5 bonds, so we have to break one bond. And the electrons are going to flow to something that wants electrons. And in this case, our oxygen already has a positive charge, so these electrons are going to fall down to that oxygen. We would break this bond. And that can't happen. If we break this bond, we've reverted back to our original structures. So no reaction happens. So for the hydrolysis reaction to happen properly, we need to have an atom adjacent to our carbonyl that's not just electronegative, but it also has to have a lone pair that's available. Because that lone pair needs to be able to reach out, right? So this reaction right here, this lone pair needs to be able to reach out and grab that hydrogen, grab that proton, so we can move the positive charge over to the electronegative atom. This way, in the second step now, right, the second real step, the lone pair on oxygen can reform our double bond, and now we see that our positive charge is over here. So we're going to break this bond, not that bond. And when we break this bond, we end up with the products that we want. Our alcohol and our amine. Okay, so a third big requirement of hydrolysis reactions is that on the atom is that we need a lone pair on the adjacent atom. So this nitrogen needs to have a lone pair so that this step right here can happen, so that nitrogen can reach out and grab that proton. By doing so, we are moving the positive charge onto that nitrogen, so then when we reform our double bond, right, this step right here, when we reform our double bond, we break the correct bond. Okay, so what I'm going to do here is go through one more example of this reaction, just straightforward, so you can see it one more time and get more comfortable with drawing out these reaction mechanisms, these pathways. Okay, this time I'll use an ester. When you're doing this, make sure you're showing your electrons, you're showing your lone pairs so that you know exactly what's happening. And again, I always encourage you to draw these things out so that you have the nucleophile oriented towards the electrophile. Okay, so the first step is we have nucleophilic attack onto the electrophile, moving electrons up to this oxygen. When we do this, we create an intermediate where this oxygen has a -1 charge, and the oxygen from water now has a +1 charge. In the second step, we need to move the positive charge from this oxygen over to this oxygen. So we reach out with this lone pair and move these electrons over. When we do that, we end up with a similar structure. The only difference is the placement of that hydrogen and therefore the placement of the positive charge. And in my final step, we reform the double bond, so this lone pair recreates that double bond, and the electrons move towards that positive charge. So we break this bond. And we end up making two products. We make a carboxylic acid, and we make an alcohol. Okay, so as I said in the last video, practice these. Practice these a lot. Get comfortable with drawing these mechanisms. In terms of identifying what functional groups are susceptible to hydrolysis, you're really thinking about these three guidelines. You need to start with a nucleophile and an electrophile. And our electrophile typically is a carbonyl. We need to have at least two electronegative atoms around that central electrophile. That's what makes it the electrophile. Okay, and finally, on the atoms adjacent to your carbonyl or your electrophile, you need to have a lone pair so that we can do this step right here. In the next video, we're going to see one more type of reaction that's very much related to hydrolysis. The mechanism is essentially identical, but it's the reverse of this. It's going to be a condensation reaction that produces water instead of using it.